Smart Wearable Biosensors, how flexible devices monitor health in real time. Why continuous health monitoring matters. Continuous monitoring of physiological parameters is very important for health monitoring, disease diagnosis, and treatment. In the past, medical devices often used bulky wired systems or battery-powered devices that needed frequent recharging. This limited comfort and movement. Wearable biosensors offer a new approach. They allow non-invasive monitoring and can continuously track signals such as heart rate, temperature, and other physiological indicators. Modern systems combine multiplexed biosensing, microfluidic sampling, and Internet of Things connectivity. Even though this technology is advancing quickly, cohort validation and performance evaluation are still needed to support clinical acceptance. In this presentation, we will discuss what wearable biosensors are, how they work, which materials make them possible, how they are fabricated, and what challenges remain for the future. What is a wearable biosensor? A wearable biosensor, or WBS, is a device worn on, inside, or near the body that continuously monitors physiological and biochemical signals. These systems are designed to be lightweight, flexible, low cost, and able to conform closely to the body. Wearable biosensors are classified into three main types. Motion state sensors measure physical activities such as gait, sleep, or tremors. Biophysical sensors measure parameters like heart rate, blood pressure, and temperature. Biochemical sensors measure biomarkers in biological fluids. These are more challenging because biological fluids are complex matrices, which makes it difficult to detect a specific target analyte. This classification helps us understand the different sensing challenges and applications in wearable technology.
Slide 3. How a biosensor works. A biosensor is an integrated, self-contained device that uses a biomolecular recognition system close to a transducer to deliver quantitative or semi-quantitative analytical data. It has three main components. First, the sensor element, also called the biorecognition layer. This may be an enzyme, antibody, nucleic acid, or another biological element that specifically interacts with a target molecule. Second, the transducer. This converts the biological interaction into a measurable signal. Third, the electronic system, which includes signal amplification, processing, and display. When the target molecule interacts with the sensor element, it causes a physical change, such as a change in conductance, resistance, absorbance, or capacitance. The transducer converts this into an electrical signal. For a biosensor to work well, it must have high sensitivity, low limits of detection, selectivity, repeatability, and durability. Based on the detection mechanism, biosensors can be classified as electrochemical, optical, calorimetric, piezoelectric, or amperometry biosensors. Two major types, electrochemical versus optical. The two main categories discussed here are electrochemical and optical biosensors. Electrochemical biosensors rely on charge transfer and oxidation reduction reactions. When the target analyte interacts with the biorecognition element, the system generates measurable signals such as current, conductivity, impedance, or potential. These sensors can be conductometric, amperometric, impedometric, or potentiometric. They're widely used because they are easier to manufacture, have increased sensitivity, give rapid responses, and use low power. However, their performance depends strongly on the sensing electrodes, and improving electrode materials is still a challenge. Optical biosensors work through interactions between the biorecognition element and an optical field. They can operate in label-free mode, where the interaction directly produces a signal, or in label-based mode, where a fluorescent, colorimetric, or luminescent label produces the signal. Techniques such as surface plasmon resonance and evanescent wave fluorescence are examples. Understanding the difference between electrical signal generation and optical signal detection is important when comparing these two approaches.
Materials that make wearables possible. The performance of wearable biosensors depends strongly on the materials used. Organic conducting and semiconducting materials, including conducting polymers such as polypyrrole and polythiophene, provide flexibility and electrical conductivity. Nanomaterials improve electrochemical signal amplification, which increases sensitivity and selectivity. Graphene oxide can be electrochemically reduced to form a conductive layer and is used to immobilize enzymes for selective detection. Metal organic frameworks, or MOFs, support selective detection and high sensitivity in sweat monitoring. Hydrogels are three-dimensional hydrophilic polymers with cross-linked networks. They have properties similar to biological tissue and are important for biocompatibility and adhesion. Conductive hydrogels also improve signal transmission while remaining flexible. Two-dimensional nanomaterials, such as MXenes, have useful chemical and physical properties that improve sensing performance. Silver and gold nanowires provide high conductivity and mechanical flexibility for wearable devices. In all these cases, the key idea is the relationship between materials' properties, such as conductivity, flexibility, and biocompatibility, and sensing performance. From materials to real devices. To turn these materials into real devices, advanced fabrication methods are needed. Miniaturization is important so that sensors are comfortable and suitable for long-term wear. Wireless communication technologies such as Bluetooth, NFC, and radio allow data to be sent to external systems and cloud-based platforms. Skin adhesion is also critical. Without close contact between the sensor and the skin, the signal-to-noise ratio decreases. Double-sided skin-sensitive conductive hydrogel-based adhesive layers help maintain adhesion while reducing irritation. Advanced printing techniques, including 3D printing and direct ink writing, allow precise fabrication of flexible sensors. Microfluidics integration, often using materials such as PDMS, allows controlled sampling and movement of biological fluids like sweat. Wearable microfluidic chips make real-time monitoring possible without invasive blood sampling. Together, miniaturization, adhesion, printing, and microfluidics make practical wearable systems possible. Future directions and real-world challenges. The future of wearable biosensors increasingly involves machine learning and artificial intelligence. ML-assisted electrochemical sensors, lab-on-a-chip sensors, electrochemiluminescence sensors, colorimetric sensors, and wearable sensors all benefit from advanced data analysis. Wearable aptasensor technology combines wearable devices with aptamer-based detection systems for real-time health monitoring. However, several challenges remain. Data accuracy and calibration are essential to ensure reliable measurements over time. Energy efficiency is necessary for long-term use, since limited power capacity restricts continuous monitoring. Data security and privacy are major concerns because sensitive health data must be protected. Large-scale validation through multidisciplinary collaboration is required before these devices can be widely adopted in medicine. Wearability requirements can limit system features, and thermal problems from peak power operations can affect comfort and performance. In addition, environmental, mechanical, chemical, and electrical factors can influence the data collected. This creates a need for advanced data analytics and multi-sensor fusion to correctly interpret and filter signals. Overall, wearable biosensors have strong potential for continuous health monitoring, but their success depends on combining material science, electronics, data science, and clinical validation into reliable and stable systems.